Welcome everybody. Hello out there. We're going to start off here. This is our first lecture in thermodynamics. And so we got set up here, and again, my goal here is to try to replicate what I would normally do in a lecture. So I've got a tablet here. I can display the PowerPoint slides that I would normally show. I've got paper behind it to simulate, some scratch paper to simulate a whiteboard. And I normally work off of a smart board, but I can just pull in and draw here on the slides as I would on a smart board. So what would I suggest for you? I would suggest have some paper handy and be ready to take some notes. Probably have your book not too far away, and typically you'll probably also want a calculator. And probably some kind of internet device wouldn't be a terrible idea. There will be times that I will say, well, pause, answer this question, and then start back up. Right? I won't do that real often, but here's the basic idea. If you're just sitting here watching videos of me talk, do some things on some PowerPoint slides, maybe work some example problems, I don't know how much you're going to get out of that. Just like if you were sitting in class, unless some of you could possibly sit in a classroom and just watch and get everything you need out of that. Majority of you need to probably be doing something active. If you're like me, you'll probably just fall asleep if you're just going to sit there and watch YouTube, 15-minute YouTube videos of me talking about thermodynamics. I try to be interesting, but I'm not going to promise I'm interesting enough to keep you awake. You probably want to be taking notes. You probably want to pause this from time to time. There'll be times you maybe want to speed it up. I don't know. But if you'll take notes, that tricks your brain into thinking, hey, this is important, or it triggers your brain into thinking, hey, this is important enough. You're processing it 3 or 4 different ways. You're hearing it, you're seeing it, now you're writing it, and you're reading it back as you write it. That tells your brain this is important. Okay, so take some notes. If you've not had, again, just like you were sitting in a lecture with me, that's my goal of these videos, is to try to replicate that. Okay, plenty of that. I'll break these up into 15-minute videos. That's just because this camera that I'm using breaks these up into 15-minute videos anyway, so I've got an alarm will go off here in a minute. What I normally do when I first introduce the idea of thermodynamics, and I can write some things on the tablet here, but a lot of it I'm probably just going to write on paper, because as terrible as my writing is, it's a little better on paper than it is on the tablet, I think. So this is thermodynamics. It's an introduction to thermodynamics, a thermodynamics 1 course, if you will, expanding on what you should have already learned in physics, calculus-based physics. We'll use some calculus principles. I will expect you to have some exposure to chemistry. Okay. Now, thermodynamics comes from 2 Greek words, and you have the internet in front of you there. You can check this out and learn more about it than I'm going to explain. I do not speak Greek, nor do I claim to be an expert there, but from what I understand, there is a Greek word, thermi, right? And of course, it's not in using Arabic or Germanic English letters there. It would be using Greek letters, but roughly thermi, and roughly the word dynamikos. I believe there's an accent there. Thermi essentially refers to heat. Dynamikos essentially refers to power or motion. Right? So the whole idea, the whole science of thermodynamics was born, as best I can understand, around the time of the Industrial Revolution. In this time frame, you have these awesome new devices begin to show up called steam engines. And the idea of a steam engine is I can apply heat into this engine, and then that heat will cause parts of that engine to move, and as those parts of the engine move, I can hook up a flour mill or a textile mill or other machinery to the moving parts. So as I heat up water or air or something within this engine, that substance wants to expand, and that causes motion within the engine. And if I can set the engine up in such a way that that motion repeats over and over again, I can then use that motion to extract power. So the idea of thermodynamics is using heat to generate power or work. Right? So in your physics class, you would have talked about work, kinetic energy, potential energy. Here we're going to introduce also heat and what we call internal energy. That's the thermal energy within the molecules. And how can I turn the thermal energies into mechanical energies? That's the whole idea here, the whole goal of the entire course. Now, it's governed. There are actually 4 laws of thermodynamics, but the 2 main laws that we will discuss. There is a 0 law, there's a first law, a second law, and a third law that we will talk about throughout this semester. Let's talk about the first 2 laws. So the first law of thermodynamics tells us that if I look at the total rate of energy in, and subtract from that the total rate of energy out, that equals the change in the energy of the system with respect to time. I always like to say, in minus out equals change. It's a conservation principle. The first law of thermodynamics is essentially the conservation of energy principle. Energy in minus the energy out has to equal the energy change. Energy cannot, and normally I would write that equation here if it was on PowerPoint slides on Smartboard, but the idea is energy cannot be created nor destroyed, it can only change forms. That is the first law of thermodynamics. The second law, now again, I'm showing you these in a differential equation form. And the second law is actually a differential inequality. I'm showing them to you in differential form. Don't worry, I'm not expecting you to have differential equations already. That's not part of the prerequisites. But to show you a differential in an expression, you should have seen a little bit of that in your calculus course, at least especially when you're talking about doing integrals. This just represents a change. This represents a change in energy within our system. This represents a change in time. That's ds dt, or I'm sorry, dE dt. This is ds. This represents the change in a quantity we call entropy. Right? And the second law says that essentially entropy is always increasing. The change in entropy is always going to be greater than or equal to the amount of heat transfer per unit temperature that causes the entropy change. So entropy, hopefully you learned a little bit about entropy in your chemistry class. I don't expect you to be real fluent in that. That's okay, just some introduction to it. Entropy represents the chaos or unpredictability of molecules. The second law, and just kind of a rough Wikipedia explanation here, is roughly saying that if you leave a system alone, an isolated system will evolve to a state of maximum entropy given enough time if you just leave it alone. What this does is it dictates, it controls the direction that heat can move. The first law really doesn't control how much heat can move in what direction. The second law controls that. And the second law says, well, you can move heat in or out. This can be positive or negative so long as you generate more entropy than what you move around. So I keep a cup of water here next to me because otherwise I'll get dry and my throat will get dry and I'll lose my voice. That water I pulled out of my refrigerator, and that refrigerator cooled that water down, so that refrigerator removed heat from the water, causing the molecules to be less chaotic. So I can decrease the entropy of that water, but what we're saying here is as long as this quantity is still larger than this heat divided by the temperature at which that heat occurs, it's fine. This is a limit. It controls the amount of energy. Again, the whole idea of thermodynamics is let's turn heat into power. And the first law would say, well, you take all of that heat in and you can make all of that power output. As long as this is zero, that's fine. And the second law says, no, you can't do that. You have to do something else because you're generating entropy in everything you do. And at best, the entropy change is equal to the heat per temperature. but in everything we're going to build, it's going to be more. Now, that's pretty deep there, and again, don't worry about the differential equations. I'm not, or differential inequality in this case. I'm not expecting you to be fluent in those. So, a thought question here. With that in mind, now that you understand a little bit about what is thermodynamics, where do you use it in your everyday life? And I want you to pause here. Pause. I've got 4 minutes left on my recording, so I don't want to stop this recording, but I want you to pause, hit the pause button here, and answer this question. Pick at least 3 places today, just today, that you think you've used thermodynamics. Go ahead and pause and come back. Okay. So I'm hoping you've got at least 3 places where you've used thermo today. Anytime that you've moved energy around or you've done something with energy, I can tell you common places not everybody thinks about is electricity. Right? Electricity is where you use moving electrons to transmit energy. Right? So that's moving energy from one location to another. And most likely it was probably originated from some kind of heat source, maybe a nuclear power plant, maybe a coal-fired power plant. Here in our part of the country, we've got a lot of natural gas or methane-fired power plants. But there's also some wind turbines and some solar cells that are also generating electricity. So in all cases, you're turning one type of energy into another. That is thermodynamics. This time of year, maybe you've got your air conditioner on, or maybe you've got some sort of heat source. You know, if you happen to be watching this in the southern hemisphere, or another time of the year where you've got a heater on, you probably have some kind of heater going, maybe cooking. You guys see now why I'm writing on paper for the most part. But we could cook. Any kind of cooking is going to require some kind of thermodynamics. So there's all kinds of applications. Here in our part of the country, first thing you want to do is look at the weather. It doesn't matter what time of year because it could change so rapidly and so violently sometimes. Weather is pure thermodynamics. Right? And I like having conversations with my meteorology colleagues because we talk the same language a lot of times, very similar language. It's a little different. Where our goal is to get power out, their goal is to look at pressure gradients and wind velocity gradients. But it's still based on heat and temperature gradients. Okay, how am I on time here? Okay, we got a minute or so. Let's see what else we can get done. Okay, one more time I want you to hit the pause button. And I want you to look up, do a little quick research. Figure out what is the difference between dimensions and units. Right? What is a dimension and what is a unit? Because those are not the same. So pause, come back, tell me what is the difference between dimensions and units. Okay, you got it? All right, so roughly, this is how I think about it. A dimension is something to be measured. And a unit is a standardized quantity used to measure a dimension. So what does that mean? Well, a meter is the standard unit that we would measure length. Now here in the United States we also use feet and inches, but everywhere else in the rest of the world would use a meter or some variation of the meter, a centimeter or a kilometer, etc. Okay? So a meter would be a unit, dimension would be length. All right, you're going to hear a pop here. I got to stop this video and then we'll restart on the next one. So loud pop.